Hi, you guys. So we're jumping into the next unit, Unit 2, okay? And what I want you guys to do for this lesson, it's a little bit different, but I'm going to ask that you guys don't take notes, okay? I'm going to go over this exploration pretty quickly, so you're definitely going to have to pause and play wherever you need to. But remember, the purpose of today's lesson is for you to just comprehend, follow along, and understand what's going on. Okay? There's no need to write it down. So here we go. So suppose I gave you guys a graph. Okay, here's the x and the y axis. And then I gave you the most popular curvy function. Okay, f of x equals x squared. This is not to scale, okay? So, for instance, if I made a marking right there and I called it 2, can you guys tell me what the y value is? Right? So, what you would do is you would take that 2 value, you would plug it into your function, and then you would get 2 squared, which actually comes out to 4. So I know that's going to be 2 comma 4. Okay, let's try this one more time. Now, what if I plugged in 5? What would that y value be? Pause and play when you're ready, okay? So if you plug in 5, and you don't have to write it out, right? Most of these can be done mentally. So this comes out to 25. Okay, let's do another one here. Now, what if you're at -6? Right? Pause and play when you're ready. If you plug in -6, the quantity -6 squared should give you positive 36. Okay, and here's one more. What if I gave you 4 plus h? Okay, what would that point look like, right? So I'll write it in red right here. What would the x coordinate be? Okay, so the x coordinate, you would just write 4 plus h, right? A little bit weird because usually it's just numbers, but now we're dealing with a parameter or a variable. But what would the y value look like? Pause and play when you're ready, okay? So if you were to plug in 4 plus h into your x, you should get the quantity 4 plus h squared. So I'm just going to put that right there. Now we can expand it, but we're just going to leave it in that factored form, okay? Okay, so what's my point? So think about this here. Let's say I draw that one more time. Okay, I have my x and my y axis. I have our favorite curvy function. Okay, f of x equals x squared. Not to scale. I am going to choose a point. I'll call it 3. Okay? Think about what that point would look like. Play when you're ready, okay? So that would be 3 comma 9, because 3 into 3 squared will give you 9. Okay, we're going to call this our anchor. Okay? So if you're not aware, an anchor is something that you use on a boat or a ship. You throw it overboard so that your boat doesn't move, right? So we're not going to move this point. This point here is going to stay where it is, and we're going to use this point every single time. Now, I'm going to pick another point. Let's call this 5. Right? Pause and play and think about what those coordinates will look like. Okay? So, that should be 5 comma 25, right? So now what I'm going to do here is I am going to connect these 2 points to the point where it looks like it creates a line, but more specifically, a line that intersects the curve twice. Do you guys remember what that's called, right? When a line intersects a curve twice. So, play when you're ready. It's called a secant line, right? So what we're going to do here is we're actually going to find the slope of this secant line. All right? So, if you remember back in Algebra 1, slope, the variable we used for slope was m. And I'm going to put in a little subscript here. We're going to find the slope of the secant line when we're given 3 comma 9 and 5 comma 25. Okay, so here we go. To find slope, that's just y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Again, replay if you have to, okay? So this comes out to 16 over 2, which comes out to 8. So the slope of that secant line right there is 8. It rises 8 and it runs 1. Okay? Now, let me change this up a little bit. Instead of 5 comma 25, okay, what if I picked a different point? What if I picked 10? Again, this is not to scale, right? Pause and play when you're ready to tell me what that point will look like, okay? 10 should have a y value of 10 squared, which is 100. So let's try this one more time. I am going to connect my anchor with my new point. So I'll use a different color here. So that orange line, notice how that orange line intersects the curve twice, so we call that a secant line. And what I'm going to do is, with a secant line, I could always find the slope. Okay? So for the slope of a secant line, let me bump this down so we have space. For the slope of a secant line, we have 2 points. We have the anchor, and then we have the new point, 10 comma 100. And with 2 points, we could always find the slope of a secant line. Remember, that's also known as the average rate of change. So here we go. That's going to be 100 minus 9 all over 10 minus 3. That's going to be 91 over 7, which comes out to, I think it's 13. Okay, so the slope of that secant line with those 2 points is 13. Cool? Okay, so let's do one more. We're going to keep our anchor, but now I am going to pick a new point. I'll call this negative 5. Pause and play when you're ready. That should be negative 5 comma positive 25, because when you square numbers, it always comes out positive. Okay, so now that I have my anchor in my new point, these 2 points I can always create a line. But specifically, this is a line that intersects a curve twice. And what do we call that? We call it a secant line. And with the secant line, we could always find the slope of it, okay? So here I have negative 5, 25 with our anchor 3 comma 9. And with 2 points, we could always find the slope of the secant line. So that's going to be 9 minus 25 all over 3 minus negative 5. That's going to give me negative 16 over positive 8, which is a negative 2. So the average rate of change, or the slope of the secant line, is negative 2. Okay? So is there a way for me to find out all of the slopes for any generic point with my anchor at 3, 9? Okay? So here's what we're going to do. I'm going to go ahead and make some space here so that you guys don't get confused. Let's say I keep my anchor, but now what I want to do is I just want to pick some generic point that's away from my anchor. So notice how my anchor is at an x value of 3. So I'm just going to move some arbitrary distance away from 3. So 3 plus however much I want to move over. 3 plus h. Think about this here, okay? Pause and play when you're ready. What would the x and y coordinates look like here? Okay? So the x coordinate should be 3 plus h, and the y coordinate should be 3 plus h quantity squared. Okay? So if I take those 2 points, that red point and the purple anchor, I could create a line, but more specifically, a line that intersects the curve twice, also known as a secant line. And with the secant line, I can always find the slope of it. So here I have 2 points. I have 3 comma 9, and I also have 3 plus h quantity squared. Okay, so here we go. So that's going to be y2 minus y1 all over x sub 2 minus x sub 1. All right, so 3 plus h quantity squared, if you expand that, remember the shortcut, or if you want to FOIL, but that takes a while, that should come out to 9 plus 6h plus h squared. And then we have a minus 9. Down below, I noticed that the 3 and the negative 3 cancels out. And then I'm just left with an h at the bottom. Okay? Even more so, I noticed that at the numerator, the 9s are going to cancel out. 9 minus 9 is 0. So here I'm left with 6h plus h squared all over h. And since I'm dividing everything by h, this actually comes out to 6 plus h, because 6h divided by h here will make that go away, and h squared divided by h will give you 1h left over, okay? So this right here, I'll use the same color. This right here is the slope of the secant line with 3, 9 as the anchor. So check this out. Back over here, my point was 5, 25. Now the question here is, if the second point is 5, 25, what is the horizontal distance from these 2 points? How far is 3 away from 5? Right? So that means my h here is 2. So check it out. If I plug 2 in here, 6 plus 2 will give me 8, and take a look at that. I was able to find the slope at that moment. Okay? Now, in your mind, you're probably going like, what the heck is Mr. Lee leading towards here, okay? Bear with me. I have a point to all of this. Now, take a look at this orange line with these 2 points, right? How far is 3 away from 10? What is the horizontal distance there? That's 7. 3 from 10, you're moving 7 units to the right. So look, if h was 7, 6 plus 7 is 13, and take a look at that. We got the slope. Okay? Now this one's different because you want to find out how far 3 is from negative 5. Okay? So h here was, you actually had to move left 8 units. Because remember, if you're looking at the picture, if you start at 3, you're going to have to go back 8 units to get to negative 5. Okay? So that's the logic behind that. So if h is negative 8, well, according to this formula, 6 plus a negative 8 should give me a negative 2. And take a look at that. We found that. So instead of me picking an infinite amount of points, I was able to come up with one generic way to finding out all the slopes of the secant lines when the anchor is at 3, 9. Big whoop, who cares, right? So what's my point? Does this work anywhere else? So, what if I have the same picture? Okay, so here we go. Let's say we were to draw out the same thing. Again, you're not writing this down, so I want you to spend most of your energy on just focusing on understanding it, okay? We have our x and y axis. We have our favorite curvy function, okay? F of x equals x squared. This is not to scale. Now, last time our anchor was at 3, 9. Now, what if I made my anchor at 4 instead? Would that change anything, right? Okay, so think about where this anchor is. Pause and play when you're ready. This should be at 4, 16 because 4 squared is 16. Now that's going to be our anchor. We're not going to move it. What if I pick the random point here, 6? Right? What would that be? That would be 6, 36. And with 2 points, I can connect it to create a line. But more specifically, a line that intersects the curve twice. We call that a secant line. And with the secant line, we could always find the slope of the secant line. So here we have 2 points. And by now, I hope you guys are getting the repetition to what I'm saying here, okay? There's a purpose behind that. So the slope of the secant line here is going to be 36 minus 16 all over 6 minus 4. That comes out to 20 over 2, which is 10. So the slope of that green line, that green secant line, is 10. Now, what if I picked a different one? What if I picked 10? Think about what that would be there. That would be 10, 100. So, if I connect that new point to my anchor again, I can create a different line, a line that intersects the curve twice, which we call a secant line, also known as a average rate of change, AROC, okay? And with 2 points, I can always find the slope of that secant line. So here we go. So the slope of that secant line is going to be 100 minus 16 all over 10 minus 4. That comes out to 84 all over 6. And if you divide that, you should get 14. Yeesh. Okay? Now, I can go all day, right? I can pick all these random points. But let's try to save some time. What if I just picked a generic point now? Right? What if I just picked some generic point? Oh no. Let's try that again. What if I picked some generic point? What would you guys call it? Okay, so some generic point that's away from the anchor. Okay, so the anchor I know is at 4, so X amount of distance away from 4 is just going to be 4 plus however much I move. Okay, now think about it. What would that point look like here? Pause and play whenever you're ready, okay? That'll come out to 4 plus h, comma 4 plus h quantity squared. Okay? Now, with that new point and that anchor, I can connect it to create a line. But more specifically, a line that intersects the curve twice. We call that a secant line. You're probably sick of my voice right now, but here we go. Let's try this one more time. Okay, so here my 2 points are 4, 16, and then 4 plus h, 4 plus h quantity squared. The slope of the secant line is going to be 4 plus h quantity squared minus 16 all over 4 plus h minus 4. If I clean that up, if I expand that perfect square there, I should get 16 plus 8h plus h squared minus 16 all over h. Okay, the 4 minus 4 goes away. And I notice that the 16 minus 16 goes away as well. I'm left with 8h plus h squared all over h. And if I divide each term by h, there I'll get 8 plus h. This is the slope of a secant line anchored at 4, 16. So let's go back and take a look. Here, okay? 4 and 6, so how far did you travel, right? Here, we had a horizontal change in 2. So if h was 2, take a look at our formula here. If h was 2, that would be 8 plus 2, which is 10, which is exactly what we got right here. Okay, now over here in the orange line, what was h? How far is 4 from 10? H right there is 6. So take a look at our formula. 8 plus 6 gives us 14, which is actually our slope right there. So we were able to come up with a very generic way to finding the slope of a secant line anchored specifically at 4, 16. In the last example, we anchored it at 3, 9. So here I ask you, can we come up with a formula where it's anchored anywhere we want it to be? Okay, so here we go. You guys shouldn't be tired because I'm the one that's talking and writing, okay? Here we go. So x and y, we'll draw out our favorite curvy function. F of x equals x squared. This is not to scale. But now, what if I just generalized my anchor? What if I just called it some x value? That would give me a point here. Pause and play. Think about what the x and y coordinate would be here. Okay, so if x is your x coordinate, when you plug it into your function here, you should get x squared. Okay? So if I move a certain amount of distance away from x arbitrarily, that would just be x plus h. Now pause and play here. Think about what those coordinates would be. That would just be x plus h, comma, quantity x plus h squared. And with 2 points, I can always create a line. More specifically, a line that intersects a curve twice. We call that a secant line. And with a secant line, we could always find the slope, also known as the average rate of change. Okay, so here we have 2 points, x comma x squared, x plus h, comma x plus h quantity squared. So here we go. The slope of the secant line is going to be y2 minus y1 all over x sub 2 minus x sub 1. So here, if I expand x plus h quantity squared, I should get x squared plus 2xh plus h squared minus x squared all over h, because the x's cancel out there. I notice that in the numerator, the x squares will cancel out as well, and I'm just left with 2xh plus h squared all over h. I then realized that I can actually divide both of those terms by h, and I'm just going to be left with 2x plus h. And this is the slope of my secant line, anchored anywhere. Okay? Think about that. So, look, if I go back to my very first example, my anchor was at 3. X was 3. So if I made x equal to 3 here, I would get 2 times 3 plus h, which is 6 plus h, which is exactly my generic formula that I got right here. Now take a look at this next example. My anchor here was at 4, 16. So that means my x value is at 4. So if my x value is at 4, that's just 2 times 4 plus h, which comes out to 8 plus h. Okay? Which is exactly the formula I got here. So I was able to come up with a very generic way to finding the slope of a secant line anywhere on a parabola, no matter where it's anchored. Okay? But I did not use any calculus yet. Okay? So I want you to think about this. What we're going to do here is we're going to go ahead and incorporate some calculus. We're going to take the limit of 2x plus h as h goes to 0. Okay. I want you to solve this first, and then we'll talk about the purpose behind that limit. If we're taking the limit as h goes to 0, this should come out to 2x. Because if h goes to 0, all you're left with is 2x. What does this mean? Okay? So before we answer that, think about what this means. Okay? So I'll break it down for you guys. Think about what h represented to begin with. When I first introduced to you guys h, what did h really mean? Right? Think about that. Play when you're ready. Think about what h really meant. H is really just how far you moved from your anchor. It's the horizontal distance from your anchor and your new point. So an easy way to remember it is h is your horizontal distance. Now, what does it mean when you're making your horizontal distance go to 0? Okay? Think about this here. If you had 2 points, okay, they have a distance between them. If you're making their distance, their horizontal distance go to 0, what does that tell you about the 2 points? Okay? And the answer to that is when you're making 2 points, right? When you're making their horizontal distance go to 0, when the horizontal distance is going to 0, eventually those 2 points are going to overlap and be right on top of each other. Okay? And when you do that, when you take 2 points, and I'll illustrate this in the next lesson with Desmos, if you take 2 points and you scoot one as closer and closer and closer as possible, eventually that secant line will turn into a line that intersects the curve only once. Okay, we call that the slope of a tangent line, also known as an instantaneous rate of change. Okay, more on that in a second. So we were able to find the slope of the tangent line here, m sub tan, of the tangent line generally anywhere. Okay, and we'll come back to that in a second. But here's the thing. Does this always work? Because all we've dealt with was with this x squared function. Does this work with any other function? So here we go. Let's run this up one more time. Here we have an x and a y axis. But now I want to use our reciprocal function here. It's called 1 over x. Now, if you don't know what that looks like, it's okay, but get to know it. It looks a little bit like this. All right, but for the sake of simplicity, we're just going to focus on the first quadrant, so I'm going to go ahead and get rid of that third quadrant graph. Okay, so here we go. I'm going to set an anchor. Let's pick the number 3. Now, keep in mind, you guys, we're dealing with a different function, okay? So if the x-coordinate is 3, what is the y-coordinate? Pause and play when you're ready. So if you plug 3 into your function here, you should get 1 over 3, okay? Let's call this our anchor. All right? So let's pick another point. Let's call this 7. Actually, no, let's just do 6. Okay, it doesn't really matter what point you pick. If that's 6, that's going to be 6 comma 1 6. And with 2 points, you could always create a line, but more specifically a secant line. And with the secant line, you could always find the slope of it. Okay, so here we go. We have 2 points, 3 comma 1/3 and 6 comma 1 6. And we're going to find the slope of a secant line. So that's going to be y sub 1 minus y sub 2 all over x sub 2 minus x sub 1. All right. So if you take a look at the numerator, you're subtracting fractions here. For the sake of pattern, I will do it the longer way. You could easily multiply by 2 to the second fraction, but I'm going to go ahead and multiply this by 3 on the top and the bottom. And here I'm going to multiply by 6 at the top and the bottom. Okay? This is going to give me 3 over 18 minus 6 over 18 all over 3. Okay? Keep going. This is going to be negative 3 over 18 all over 3. Now, there's an invisible over 1 there. How do we divide fractions? We multiply by the reciprocal. So here we go. Some people like to call it KFC, Kentucky Fried Chicken. I really hate that. You divide a fraction by multiplying by the reciprocal. Okay? I notice that I can cross-reduce the 3's there. And I'm going to be left with negative 1 over 18, which is our slope. Okay? Messy answers, but who cares? Now, I'm going to fast forward here. I could pick a different point, but let's speed this up to see if it works. What if I picked some generic point anchored away from 3, right? What would you guys call this right here? Think about that, play when you're ready. I would call this 3 plus however much you're moving. So what would the point be here? It would be 3 plus h, comma, think about that, you guys. It wouldn't be 3 plus h quantity squared because we're not dealing with that function, okay? This is going to be 1 over 3 plus h. And with 2 points, I can create a secant line. And with the secant line, I can always find the slope of it, okay? So the slope of the secant line at 3 comma 1/3 and at 3 plus h comma 1 over 3 plus h, that is going to be 1 over 3 plus h minus 1/3 all over 3 plus h minus 3. I'm tired of talking, but let's keep going. I notice at the top I'm subtracting 2 fractions, so I need to get common denominators, so I'll multiply top and bottom by 3 here, and 3 plus h on the other fraction. So I'm going to get a common denominator of 3 times 3 plus h. On the top, I'm going to have 3 times 1, which is 3, minus 1 times 3 plus h. If I distribute that negative 1, I should get 3 minus 3 minus h all over 3 times 3 plus h. I won't expand the bottom, okay? There's a reason why. So I noticed that 3 minus 3 up top is going to go away. I'm going to be left with a negative h all over 3 times 3 plus h. Okay, so this is the generic slope of a secant line anchored at 3 comma 1/3. So let's check it out, see if it works. If I take a look at this anchor, what is the horizontal distance from 3 and 6? H there would be 3. So let me plug this in here. Well, if h is 3, I'm going to have negative 3 all over 3 times 3 plus 3. That'll give me negative 3 over 3 times 6, which is 18. What am I missing? Uh-oh, I think I made a mistake. Uh, what am I missing here, you guys? Oh, okay. I'm sorry. Silly rabbit. Okay, right here. I totally forgot. Down below, I totally neglected this. 3 minus 3, okay, goes away, and you're just left with an H. I forgot to bring that over. Come on, Mr. Lee. Okay, so let me backtrack a bit. Here we go. So here we're dividing fractions. How do we divide fractions? We multiply by the reciprocal. So here this comes out to negative h over 3 times 3 plus h times 1 over h. And I noticed that I could actually reduce out the h's right there and be left with negative 1 over 3 times 3 plus h. That looks a lot better. Okay, so going back, remember 3 and 6 has a horizontal distance of 3. So if h is 3 here, if I plug that in, I'll actually get negative 1 over 3 times 3 plus 3, which comes out to negative 1 over 18, which is exactly what I got right here. Okay. Whew. So, what was the point? I was able to come up with a generic way to finding the slope of a secant line for a point, any point that's on this rational function or reciprocal function. Is there some way where I can find out the slopes of all secant lines at any anchor? So, we're almost done, you guys. Here we go. Let's say we had an x and y axis and we had that same reciprocal function one more time, okay? But now, let's make it very general, okay? So if I want to pick any general anchor point, I'm going to call it x. So what would the coordinates be there? Pause and play when you're ready. That'll be x comma 1 over x. And if I want to pick any generic point away from x, that's going to be x plus h. So that'll be x plus h comma 1 over x plus h. And with 2 points, even though it's generic, 2 points I can create a line, specifically a secant line. And with the secant line, I could always find the slope, also known as the average rate of change. So with x comma 1 over x and x plus h comma 1 over x plus h, the slope of the secant line will be 1 over x plus h minus 1 over x all over x plus h minus x. Up top, I'm going to get common denominators and multiply by x, and then x plus h right over here. That'll equal, and before I forget, down below is going to come out to h. Up top, I'm going to get a common denominator of x times x plus h. And over here, 1 times x is going to be x minus 1 times the quantity x plus h. If I distribute that guy, I'm going to get x minus 1x minus 1 of the h's all over x times x plus h all over h. All the numbers seem to have disappeared. Oh no. Okay, here we go. X minus x up top goes away. You're left with just a negative h all over x times x plus h divided by h. But when you're dividing a fraction, that's the same thing as saying negative h over x times x plus h times 1 over h. Remember, you're just trying to comprehend. You don't have to write this down. The h's end up reducing, and I get negative 1 over x times x plus h. Okay, what the heck is this? This is the slope of a secant line at any point, or at any anchor, I should say. Okay, so take a look. Let's go back. Originally, our anchor here was at 3, so x is 3 here. Let's go back. If I plug in 3 for x, I will get negative 1 over 3 times 3 plus h, which is exactly what I got for the general secant slope of a secant line right here. So I was able to come up with a generic way for the slope of a secant line at any anchor. Right? Okay, we haven't done any calculus yet. Let me write that out one more time. The slope of a secant line is negative 1 over x times x plus h. Now, if I apply some calculus here, what if I take the limit as h approaches 0 for this function right here? Okay? You guys were taught that when you're given a limit, you try to plug and chug right away. So if h is going to 0, I will get negative 1 over x squared. But think about it. Negative 1 over x squared is what happens when h goes to 0. So let's talk about this one more time. What does it mean when h goes to 0 graphically? Play when you're ready, okay? When h goes to 0, your 2 points are getting closer and closer and closer to each other to the point where they will overlap. And when these 2 points overlap, they no longer become a secant line, they actually become a tangent line. So this right here is actually the slope of a tangent line. Okay? So what the heck is my point? So remember that conversation back in the last lesson? How do you rise and run, or how do you find the slope when you only have one data point? Right? When you have 2 data points, it's easy because all you have to do is rise and run, right? But how do you find the slope of something if you're only given one moment? What you guys are doing right now with me is you're learning how to use that radar gun that police officer used. Okay? You're learning how to capture how fast something is moving at one particular moment. Okay? So, I used a quadratic function, x squared, and I found out a generic way to finding the slope of a tangent line. I was able to use it for this reciprocal function here. Now the question is, does it work for all functions? So, more on that later, but can we generalize this even more? Here's the last one, I promise. Okay, here's your x and y axis, right? Now instead of picking a specific function, what if I just gave you some random function? Okay? Not necessarily anything that we know, so all we know is it's called f of x, all right? Now, what if I just picked some generic point? And this is where you guys have to really think. If I'm picking a generic point, what do I call it? That should be x. So that should be x, comma. Now think about what the y value should be. Okay? The y value should just be, well, whatever f of x is. Okay? Because we don't know what the function is. Now, what if I wanted to pick a generic point away from x? What would you guys call that? That would be x plus however much I move. Right? Now, what would those coordinates be? That would be x plus h, comma, f of x plus h. It looks very weird, okay? With 2 points, I can make a line, specifically a line that intersects a curve twice. We call that a secant line. And with the secant line, we could always find the slope of it. So here we go. With these 2 points, okay, the slope of the secant line is f of x plus h minus f of x all over x plus h minus x. Now, because I don't know what the functions are, that numerator kind of has to stay the same there. So I'm just going to write f of x plus h minus f of x. But down below, I noticed that an x can cancel out, so I'm just left with h here. This is the slope of any secant line for any function at any anchor. Okay? Now, the slope of a secant line we don't care about the slope of a secant line because we learned that back in Algebra 1. That's just a linear function with 2 data points, right? So how do we make it so that we're finding the slope of a tangent line? So what you guys have to do is we're going to go ahead and take the limit as h goes to 0 for this entire thing. Okay? Think about what that means in red. Okay? When h goes to 0, what does that mean graphically? Okay? Think about that. Play when you're ready. I'm hoping you guys would have said when h goes to 0, that means that these 2 points are getting closer and closer and closer to each other to the point where they overlap. And when they overlap, they create a different line. We call that a tangent. So this is the slope of a tangent line. Now this right here, you guys, is so important to calculus that they gave it a special name. Okay? So important that it's actually our next big idea. Big idea number 2. They call this a derivative. Okay? So look, to wrap this up, you guys, you don't have to produce this, but you got to understand the logic behind it. We went from finding slopes of secant lines at several places from several functions, and we were able to generalize it. And up to the point where when we incorporated the concept of our big idea number 1, limits, when we made our 2 points get so close to each other, we notice that that secant line actually transforms into a tangent line. If you get arbitrarily close, that line will turn into a tangent line. And that is how you find the slope of a tangent line, also called a derivative, also called the instantaneous rate of change. Okay? Slope of a tangent, aka derivative. Okay? You're finding out how fast someone is driving or how fast anything is moving or the rate of their change instantaneously with one data point. So with this powerful concept, you guys can find out how fast money is moving at a particular moment. If your business is profiting on the 3rd year of your operation, how fast you're building an apartment complex at what rate, right? So how are all of those things important and how do we apply it? That goes into big idea number 2, which is our next unit. Okay? Whew, okay, I'm going to go sleep now.